Hello guys. Today we'll continue the hypothesis testing chapter. And as you saw last time, we learned in the last videos, we learned the framework for hypothesis testing. We are interested in a hypothesis about the population mean, and we restrict our focus on the population mean. And as I said in the last videos, the hypothesis testing is very exotic concept. It's quite different from the typical statistics or what you imagine as a statistics. So it's kind of unfair, and it is testing. It is mainly it's to test a pre-existing hypothesis. So it doesn't sound like statistic or doesn't sound like scientific, but uh, it is what it is. And today and in the last video, in the last lecture, the main purpose was to give you the idea how we rank the most suspicious outcomes. So when we observe an outcome and we have a belief, and we would like to measure how unlikely the observation is if my belief was true. If my belief was true, then the observation may contradict to my belief, so it's very suspicious. Then we are going to reject. We cannot reject the data itself, so we reject our belief if the contrast is too large, or if the outcome is very suspicious. So within top 1% or 5% or 10%. Today I'm going to make more formulas based on that idea, based on the same same framework. And let's start from these hypotheses. We are going to restrict the form of the hypothesis to this in this chapter. So the null hypothesis H0 is the null hypothesis. This is your existing hypothesis, saying that the population mean equals to mu zero. Mu zero is a specific number you believe. So in our previous example, I believed students study like 40 hours, like 50 hours for the final exams on average. Then 50 hours is the mu zero here. So it's usually given. You should have a specific number for a hypothesis. And the alternative hypothesis is simply the negation of the null hypothesis. The population mean is not 50 hours, for example. And we are going to consider three different ways to present the result of a hypothesis test. So there are three different ways to get to the same conclusion. Of course, the three methods are equivalent to each other in the end. The reason why I'm teaching you this is because literally the results are presented in different ways. So for example, statistical programs return different values, but actually they are the same thing. So you see, like when you run something, you may see a lot of numbers, but if you understand what's going on, then actually you will find that they are all equivalent. So typically, so the what I present here is a typical points where students and many beginners are confused when reading the result. So let me describe three different ways to present the data, or the three different forms you may see in practice. The three methods are based on different numbers. First, p-value. Second, t-statistic. And third, the critical values. So for example, a program may report a p-value as a result of the hypothesis test, or another program may present t-statistic, or another program may present critical value. So as I said, these three methods are equivalent. They are the same thing, but the numbers, how the numbers are presented, could be different from an article to another or a program to another. So, and also all of them are widely used. So it's good to understand how they are related, how they are constructed, and how to read them, how to interpret them. And of course, the reason why the three methods coexist is because one may be more convenient, more easier to calculate than the others in some cases. So you can choose one method in a specific case, and then you may change to another method if the context changes. So which may be more convenient to you. So it's also nice to understand all of them. First, let me start with the p-value approach. This is how I explained, how I introduced hypothesis testing in the previous lecture. The idea is like this: calculate. Of course, from now, of course, you have the hypothesis, and then from the data, calculate the sample average, and standardize the difference between the sample mean and your belief. So this is the standardization. We standardize X bar using its sampling distribution under the assumption that the null hypothesis is true. Then you will get this. This guy is called the t-statistic. T-statistic, usually we use t to denote this statistic. And from this t-statistic, you can calculate the probability outside the t-statistic. So probability that the standard normal is smaller than minus absolute value of t, or plus absolute value of t. Oh, here bar is missing. Sorry about that. So this probability captures the probability of outcomes that's less likely than what you observe. So first, you know this t-statistic follows a standard normal distribution. Second, you observe this guy. So when you observe this guy, you know outside of that observation is less likely, or in my term, more suspicious, more contradicting to the belief. So we are interested in how many outcomes are more suspicious than what you observe. So it's the rank. If this probability is, for example, 1%, that means your observation is very suspicious within top 1% level. Or if this p-value is, say, 50%, then half of the potential outcomes, half of the possible outcomes are more suspicious than what you observe. So your rank is in the middle. The suspiciousness is ranked in the middle. So that's how we interpret p-value. And then based on this p-value, our decision rule is like this. Our decision is either to reject H0 or not to reject H0. Always. There are only two. Yes or no. H0 is wrong or not wrong. I'm not saying it's correct, but I would say it's not wrong. So you reject H0 if p-value is too small. So p-value is too small when it's top ranked. It's, say, for example, it's top 0.1%. Then it's very small, which means it's very suspicious. Or the very top 0.1% suspicious outcome. So then you have to reject H0. Otherwise, do not reject. And alpha, remember, alpha is called the significance level, and this is your choice, your cutoff. How much you are going to reject and how much you are going to accept. So it's your choice. So that's your you have to choose it before when you set up the hypothesis testing. So as I said, the p-value is a measure of likelihood of what you observed if the hypothesis is true. So concept is a little bit more complicated than that, But basically, we would like to measure how likely your observation is relative to the null hypothesis when you believe in the null hypothesis. And remember, think about the process of to obtain the p-value. What you need is the data x bar and standard deviation s and the sample size n. So you need these information from the data. So that means you have to recalculate the p-value whenever you have a new data, which is nice. It's very nice. You have to recalculate x bar, s, n every time you have a new data. But you do not need alpha to calculate the p-value, because after calculating the p-value, you compare the p-value with alpha directly. So you don't need alpha to calculate the p-value. So it is nice because alpha is just your choice. So it doesn't need to be 1% or 5%, 10%. It's an ad hoc choice. So like if when you present one result, if one reader does not like your alpha, then the reader may change alpha as much as he wants. So still, it's very easy to make the decision or change the decision because the decision rule is simple. You can just compare the calculate p-value and your own alpha. Your own alpha is ad hoc, but you can change it easily. So that's very nice. Typically, typically this is the number one result, like most widely used result in many statistical programs, because computer does not make the decision subjectively, so does not choose alpha. It's arbitrary ad hoc decision. So they don't care about what you choose. They don't touch you in that dimension, but it only calculates the p-value from the data and the null hypothesis. So it's commonly used in many statistical programs. Okay, so the p-value is what we learned in the last lecture, and I'm going to continue some more explanation about the p-value and continue to the next method in the next video. Thanks.